recording? Okay, it's recording. All right, so let's say you're told that you had 15 grams of a substance. And in that 15 grams of substance, you analyzed it, and you found that 11.22 grams of that substance was carbon, and 3.78 grams of that substance was hydrogen. What's its chemical formula? What's its empirical formula? We're looking specifically for empirical formulas. So what we're going to do is we're going to follow our steps over here. And I'm going to go back and forth between the PowerPoint and the periodic table. All right, so step 1A, if given percentages, notice we were not given percentages, we're given grams. So we can skip step 1A. 1B says, if given grams, which is what we got, convert the grams of each element to moles of each element. So I'm going to take my 11.22 grams of carbon here and my 3.78 grams of hydrogen. I'll write them both down, and I'm going to turn both of them into moles. Okay. And you'll recall what we do to turn grams into moles is we divide by the atomic mass. So we got to look up the atomic mass. Let's go ahead and look up the atomic mass. All right. And when I look up the atomic mass in the periodic table, let's see. Oh, you know what? I'm already here for hydrogen, so let me go ahead and do hydrogen. You'll notice hydrogen's atomic mass is 1.01, if I round to 2 decimal places. 1.01 grams per mole. For hydrogen, its atomic mass is 12.01. 12.01 grams per mole. Okay, so I'm going to go ahead and turn these grams into moles by dividing by the atomic mass for both of them. For carbon, I'm going to take 11.22 grams divided by 12 grams per mole, 12.01. Let's see, 11.22 divided by, here, 12.01. Sorry if I put the calculator here in the way of the problem, but it seems like it's easier to see if I have it like in certain spots. Okay, so I got 0.9342 moles. 0.9342 moles of carbon. Okay. So all I did was took grams per mole, just like we did last week. Right? We're going to take we're going to get some practice in doing some of the things we learned last week. Now that we've learned this, we're going to go ahead and use it. The skill, we're going to use it to determine certain things. The second one, 3.78 divided by 1.01. 3.78 divided by 1.01. That's going to give me 3.743. 3.743 moles of hydrogen. Okay? So now we have moles of hydrogen. That actually was our step 2. I go to, let me go ahead and show you this right here. So that was step 1, 1B. So we convert the grams of each element to moles of each element. Make this bigger. Step 2, identify the element with the least number of moles. Carbon here has 0.9342 moles. Hydrogen has 3.743 moles. So carbon has less than hydrogen, right? So what I'm going to do then is divide the moles of each element by the least number of moles. The least number of moles is 0.9342 here, so I'm going to divide both numbers by 0.9342 divided by 0.9342. Okay. Remember, you take both the number of moles and divide by the same number, the least number of moles. Okay. Some people make the mistake of just dividing by whatever number it is, but that doesn't give you anything. That just gives you a 1-to-1 ratio, and that doesn't really mean anything. Now, when you take the 0.9342 divided by 0.9342, or whichever one you felt was the least, and so you divide by that one, that's just going to give you 1.0, right? A number divided by itself is going to give you 1.0 moles of that element. So what this is saying is for every 1 mole of carbon, there is, and what we're going to do is determine how many moles of hydrogen. Right? So if I have 3.743 moles of hydrogen, I'm going to go ahead and take that number, which is already in my calculator at this point, and divide by 0.9342. 0.9342. And what I'm going to get is 4.006. Right? Notice that it's really close. It's really close to an integer. It's almost an integer. There's 4.00. 4.0. I'm just going to round it to 4.0 moles of hydrogen. What this is telling me is that for every 1 mole of carbon, there are 4 moles of hydrogen. And remember, as I said, the subscripts in our formulas can give you the atom ratios, atoms of one substance, one element to another, or they can give you mole ratios, moles of one substance to another. So these numbers right here, this 1.0 with carbon and the 4.0 with hydrogen, those are going to be our subscripts now. So for carbon, subscript is a 1. Since we don't put down ones, we just assume that it's 1. I won't put anything. I won't write any subscript. And for hydrogen, there's a 4.0. So here's my formula, CH4. This is the formula. This is the empirical formula for this substance, CH4. Okay. And that's employing step number 3. Use the resultant numbers as subscripts in the empirical formula. Right. Whatever these numbers are, there are subscripts. The 4.0 becomes a subscript to hydrogen. The 1.0 becomes a subscript to carbon. Once you've done that, they should be whole numbers. Now, some people don't feel comfortable using moles. They're like, but wait, the subscripts, you told us the subscripts were how many atoms, what was the relative number of atoms of one element to another, not moles. Are you sure that that's the same thing? Let me go ahead and show you that we'd get the same answer, even if we kept going on with our problem and turned our moles of each element into atoms of each element. So what I'm going to do right now is I'm going to take the moles that we had calculated of carbon and the moles that we had calculated of hydrogen and turn those into atoms. So we can get the atom ratios between the two. Some people will feel better. So I'm going to write down my 0.9342 moles of carbon, which is what I'd calculated after turning the grams to moles. I'm going to turn those into atoms. And remember that what we do, we take, in order to turn moles to atoms, we multiply by Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. And if I take my 0.9342 moles times 6.02 times 10 to the 23rd, I get 5.623 times 10 to the 23rd. 5.623 times 10 to the 23rd atoms of carbon. And if I take my 3.743 moles of hydrogen, I turn that into atoms by multiplying by Avogadro's number. We have 3.743 multiplied by 6.02 times 10 to the 23rd. That's going to give me 2.253 times 10 to the 24th atoms of hydrogen. Okay. So in our 11.22 grams of carbon, there was this many atoms of carbon. In our 3.78 grams of hydrogen, there are this many atoms of hydrogen. Let's figure out what the atom ratios are here. Okay. Between this number and this number, the 5.623 times 10 to the 23rd number is smaller. Sometimes people think this is a smaller one because they see a smaller coefficient right out front. But remember, you have to look at the powers of 10, right? The exponent. That'll tell you which one. That's telling you basically what number or digit place you're looking at. And so 10 to the 23rd is smaller than 10 to the 24th. So I'm going to divide both both these numbers by 5.623 times 10 to the 23rd. Let's divide both of them by 5.623 times 10 to the 23rd. And that's going to give you, I'm going to have to write it down here. For every, well, this number divided by itself is just going to give you 1 atom of carbon for every, let's see, 2.253 times 10 to the 24th. I still have it in my calculator. I divide it by the 5.623 times 10 to the 23rd. That's going to give me 4.007. Basically the same number I got from here, 4.0 atoms of hydrogen. Okay, and so here, these numbers right here are the ones we're going to use as our subscripts. I'll take these as my subscript here, and you'll notice that that gives me the same formula, CH4, as we got above. Okay, so the atom ratios and the mole ratios are the same. Okay. There's 1 to 4 up there, 1 mole of carbon for every 4 moles of hydrogen, and it's same thing here, 1 atom of carbon for every 4 atoms of hydrogen. And the reason why is because we had moles of both. In order to turn them into atoms, we multiplied by the same number. So it doesn't change our ratio of one to the other. It ends up being the same. So whether you figure out the atoms of each element or the moles of each element, you're going to end up with the same answer in the same formula. Okay. That's the only time I'll go ahead and do all the atoms. I just want to show people that you get the same thing. Okay. But usually we can stop once you've turned grams to moles and you figure out the mole ratio, you can stop there. Okay? Any questions so far on this? All right, let's do sample problem number 2. Okay. I've got 4 sample problems to do, but because they each have their own little tricks, but that one's the one that takes the longest because I'm explaining stuff. All right, let's go ahead and do this a little bit more expedient manner. Just go through our steps. Step 1, if given percentages, assume 100 grams and turn percentages into grams of each element. Okay. So this time we're given percentages. Last time we weren't. Last time you were given grams of each. Right? We jumped straight to 1B. This time you're given percentages. And you'll see it says assume 100 grams. Why 100 grams? Well, because it really doesn't matter how much of the substance you've got, the proportions are always going to be there. And if we use 100 grams, it makes the math easier, right? What's 88.82% of 100? 88.82, right? What's 11.18% of 100? 11.18.